Section 2.3, Calculating Limits Using the Limit Laws. We've been calculating limits so far by sort of guessing using tables or looking at a graph. Now we're going to start using some more formal methods such as these limit laws. If we have a constant c and the limits as x approaches a of f of x and the limits as x approaches a of g of x, then the limit of the sum of f and g is the sum of the two limits, so you can basically split it apart. Same thing with the difference. That constant c, if it's inside the limit, you can pull it outside of the limit for law number 3. If you have the limit of a product, you can just multiply two limits. And if you have the limit of a quotient, then you can divide two limits, assuming that the denominator limit is not 0. Let's use some of these. Use the limit laws and the graphs of f and g to evaluate the following limits if they exist. First, we want the limit of f of x plus 5g of x as x approaches minus 2. So this thing can be split into the limit as x approaches minus 2 of f of x plus the limit as x approaches minus 2 of 5 times g of x. This is equal to the limit as x approaches minus 2 of f of x plus 5 times the limit as x approaches minus 2 of g of x. We can basically pull out that constant 5 out. Okay, so now let's take a look at our graph. As x approaches minus 2, so we're moving along f, we can see that that approaches 1, no matter where we travel from. If we look at g of x as x approaches minus 2, so that's over here. If we go either direction, we can see that it approaches minus 1 for the y value. So that means that this equals 1 for the limit for f plus 5 times minus 1 for the limit for g, and that adds up to minus 4. Let's do the second one. The limit of f times g as x approaches 1. So the issue here is that if we look at x approaching 1 along g, looks like we approach minus 2. If we approach from the right, it looks like we approach minus 1. So the left and right-handed limits are not equal for g. So we can't just split this into the product because one of these limits doesn't even exist. So instead, let's look at the left-handed limit. Limit as x approaches 1 from the left. That we can split because it looks like the left-handed limits do exist. Okay, so the limit of f as x approaches 1 from the left. So we're moving in over here. That just equals 2. And the limit of g we already said was minus 2. So that's minus 4. The limit as x approaches 1 from the right of this product can also be split. So again, f is the same limit from the left and the right, but g was minus 1 this time. So this becomes minus 2. That implies that this limit does not exist. Because remember, if our left and hand right limits don't exist, or don't match, then our entire limit, our two-handed limit, does not exist. For our last example here, let's look at our quotient. Well, for the numerator, as x approaches 2, f of x approaches 1.4. Yeah, it looks like roughly 1.4. However, let's look at the limit as x approaches 2 of g of x. We can see that as x approaches 2 for g of x, we approach 0. So the denominator limit here, if we were to split this, would be 0. We can't split it in that case. The limit in the numerator approaches a specific number, though. As a result of that, this limit does not exist. We're going to see later on when our numerator approaches 0, when our denominator approaches 0, sometimes the limit will exist. It becomes an indeterminate form. But for now, whenever we see a numerator approaching a specific value, denominator approaching 0, we know the limit does not exist. Let's talk about the power and root laws now. By repeatedly applying the product law and using some basic intuition, we can obtain these following laws. Limit of f of x to the n is the same thing as if we took that exponent and put it outside of the entire limit. The limit of a constant is the constant. The limit of x as x approaches a is just whatever value we want to plug in. And similarly for the limit of x to the n, that's just a to the n, assuming that n is a positive integer. Same thing for roots. The limit of the nth root of x is the nth root of a as x approaches a. And we have to assume that a is positive if we were taking an even root. And the limit of the nth root is the same thing as the nth root of the limit. And again, we have to assume that the limit is positive in this case, if n is even. Let's use these laws to evaluate a couple limits. Later on, when we're looking at epsilon delta proofs, we'll have enough tools in our arsenal to actually prove these laws, but for now we just have to take them for granted. Let's evaluate the following limits and justify each step. 2x squared minus 3x plus 4 as x approaches 5. So again, we can split this up. So we'll take the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. Okay, we can pull out the 2 and pull out the 3. So this is 2 times the limit as x approaches 4 of x squared minus 3 times the limit as x approaches... Oh wait, what did I do 4? That should be 5. Minus 3 times the limit of x as x approaches 5 plus 3 times the limit as x approaches 5 of 4. Maybe I was thinking about that 4. Okay, so now we can just plug in the 5 from one of our laws that we just did. So this would be 2 times 5 squared because it's power minus 3 times 5. And we said the limit of a constant is just the constant itself, so plus 4. Altogether, adds up to 39. Let's look at our next one. We can split this using our quotient law, because notice if you plug in minus 2 for the limit for the denominator, it's not going to end up being 0. So we'll take the limit as x approaches minus 2 of x cubed plus 2x squared minus 1 divided by the limit as x approaches minus 2 of 5 minus 3x. Okay, so now this will just be the limit as x approaches minus 2 of x cubed plus 2 times the limit as x approaches minus 2 of x squared minus the limit as x approaches minus 2 of 1 divided by the limit as x approaches minus 2 of 5 minus 3 times the limit as x approaches minus 2 of x. And that this thing equals minus 2 to the cubed plus 2 times minus 2 squared minus 1, because we're at the point where we could use our laws to just plug in, over 5 minus 3 times minus 2. Okay, and that works out to minus 1 over 11. Next up is our direct substitution property. If f is a polynomial or rational function and a is in the domain, then the limit as x approaches a of f of x equals f of a. That should make sense because for polynomials, they're just sums or differences of our power functions, which we just said that we could just plug into, assuming that you can also pull out constants. So it makes sense that you should be able to just directly evaluate these guys. Later on, we're going to see that this property is actually called continuity at a point A. For our next example, let's find the limit as x approaches 1 of x squared minus 1 over x minus 1. This limit should seem familiar. It was the one we were first looking at for a tangent line to our parabola y equals x squared. So then we could set this equal to the limit as x approaches 1 of x minus 1 times x plus 1 over x minus 1. Because if we just tried plugging in 1 to begin with, our denominator becomes 0. And we're not allowed to use our quotient law whenever our denominator is 0. However, remember that by definition, we evaluate limits nearby a point, but not at the point itself. So we're not going to actually consider x values where x is equal to 1. So that means that we can cancel out the x minus 1 on top and bottom because x is not equal to 1. So we get the limit as x approaches 1 of x plus 1 all by itself because the x minus 1's cancel, which is just 1 plus 1. If f is equal to g when x is not equal to a, then the limit of f is equal to the limit of g as x approaches a, provided that the limit exists. So if two functions have the same values except where we're looking at the limit, then their limits will still be equal. So let's do an example. Let's find the limit as x approaches 1 of g of x, where g of x is x plus 1 if x is not equal to 1, and it's pi if x is equal to 1. Okay, so since g of x is equal to x plus 1 whenever x is not equal to 1, that implies that the limit as x approaches 1 g of x will be equal to the limit as x approaches 1 of x plus 1, because they match whenever we're not looking at the value that we're approaching for our limit. Because two functions match, their limits must match. So that means that that original limit must be equal to 2 because the limit of x plus 1 as x approaches 1 is 2. It's a polynomial, we can just directly substitute. Okay, how about the limit of 3 plus h squared minus 9 over h as h goes to 0? So let's try expanding this a little bit. Realize we can't plug in 0 because we'd have a 0 in our denominator. So let's look at this limit if we actually expand the 3 plus h squared and get 9 plus 6h plus h minus 9. Keep r over h. Okay, so now we've got 9 minus 9 on top, so we can just subtract those. So we end up with 6h plus h squared left over. And we can pull out the h by factoring it out in the numerator. Again, we're not looking at values of h where h is equal to 0, we're only looking at it nearby 0. So that means h cannot be 0, so we're allowed to divide by it. So it'll cancel on top and bottom. So this will just be the limit of 6 plus h. That's a polynomial, so we directly substitute and get 6. Let's find the limit of the square root of t squared plus 9 minus 3 over t squared as t approaches 0. Again, can't plug in 0 yet, but we could probably manipulate this thing algebraically to a form where we can cancel something. So let's say we've got this thing is equal to the limit as t approaches 0 of square root t squared plus 9 minus 3 over t squared. I can't really factor out a t squared, but it looks like we have a radical in our numerator. And whenever you see a radical, it's always like a hint. You might want to try rationalizing it to see if that makes it better to deal with when it's in a fraction. So we rationalize the numerator. Instead of minus 3, we change it to plus 3. Since we're multiplying it by on the top, we have to also multiply it by it on the bottom when we rationalize. Okay, so we multiply the top out. We get t squared plus 9 minus 9. And on the bottom, we get t squared times that whole mess. I'm not going to bother multiplying it out yet because I'm hoping that I can cancel out t squared, right? Because look, if we have this plus 9 minus 9, that's just t squared. Okay, so that's awesome. We can cancel out the t squareds and just get that this is the limit as t goes to 0 of 1 on top, square root t squared plus 9 plus 3. Okay, so now I can take the limit and I can put it on top and bottom, because notice the limit in the denominator will not end up being 0. So the limit on the top will just be 1. On the bottom, it's the sum of the limits, so I can do the limit of the square root and the limit of the 3 separately. So that just becomes 3. Because it's the limit of a square root, I can put the limit inside the square root. And limit of 3 is just 3, like I said. Okay, so then this ends up becoming 1 over, well, when we plug in, because the limit of t squared plus 9, that's a polynomial, we can directly substitute. So that becomes 3, because the plugging in 3 squared is 9 plus 9, 18. becomes 3 because we plug in 0. 0 squared plus 9 is just 9. Square root of 9 is just 3. Plus 3. So this is 1/6. Next, let's show that the limit of the absolute value of x as x approaches 0 is 0. Remember that we defined absolute value of x to be a piecewise function, x, if x is greater than or equal to 0, and minus x if x is less than 0. That way, any negative numbers get another negative to cancel them out and become positive. We want our absolute value to always be positive. So let's look at our left and right-handed limits. If we look at the right-handed limit of absolute value of x, that means that we're going in from above 0. So we're only looking at this first rule for our piecewise function. So that means that we're only considering x where the absolute value of x where it equals x. So we can just plug in and get 0. Similarly, if we look at 0 from the left, that means we're looking at negative values. So that means we're looking at the negative definition for our absolute value function, which is minus x. And again, we can plug in and get 0. Since these two limits agree with each other, that implies that the two-sided limit is also 0, because it has to agree with the left and right-handed limits when they agree. Let's prove that this limit doesn't exist. So it's the limit of absolute value of x over x as x approaches 0. Again, let's look at the left and right-handed limits. So let's look at the limit as x goes to 0 from the right of absolute value of x over x. That's the limit as x goes to 0 from the right of x over x, because we're looking at positive values, so we use the positive definition. And x divided by x equals 1, because x cannot be 0. Remember, we're taking a limit near 0, not equal to 0. Okay, so that limit is just 1, because the limit of a constant is itself. Let's look at the left-handed limit. So we use the negative rule in this case. We have negative x over x. So that means that the limit as x approaches 0 from the left is the limit of minus 1 when we cancel. So that's equal to minus 1. So these limits do not match. So that shows right off the bat that this limit does not exist. This could also be clear if we look at a graph. Remember that for positive values, this function will become absolute value of x over x. It'll become x over x, which is just 1. Right? We can't look at it at 0 because it would be undefined. If we look at negative values, then it's minus 1. So it makes sense, as you move in from the right, you get closer and closer to 1 because you're equal to 1 the entire time. As you move in from the left, you get closer and closer to minus 1 because you're equal to minus 1 the entire time. So those left and right sides definitely don't match up. Let's see if f of x equals square root of x minus 4 when x is greater than 4, and 8 minus 2x when x is less than 4. Let's determine whether this limit exists. Again, whenever we see these piecewise functions, it's usually a good idea, when they're defined at the piece where our limit is being taken, to look at the left and right-sided limits. So first we look at the right-sided limit. And we use the right definition then, the first one. So it's just square root of x minus 4. We plug in 4 because we can put our limit inside of our square root, and then it's a polynomial, so it becomes square root of 4 minus 4, which is 0. If we look at the limit as x approaches 4 from the left of f of x, then that becomes the limit of a polynomial, which we love because we can just use direct substitution and get 8 minus 2 times 4, which is 8 minus 8, which is 0. Ah, so the limits agree. That's wonderful. So that means that the two-sided limit exists and is equal to 0. Again, we could take a look at a graph to verify this. Okay, so it's 8 minus 2x until it gets to 4. And then it goes and becomes this square root function. And yeah, it makes sense. If you go in from the left or the right, you still approach 0 either way. Let's talk about our greatest integer function. The greatest integer function is defined by a greatest integer function of x, where this greatest integer function is the largest integer that is less than or equal to x. For instance, the greatest integer function of 4 is 4. For 4.8, it's 4. For pi, it's 3. For rad 2, it's 1. For minus a half, it's minus 1. Basically, whatever number we take, if it has a whole bunch of decimals after it, we cut off all those decimals. We just leave it the integer. So it's the closest number that's smaller than the number. If we think about integers, the closest integer smaller than the number. We sometimes call this the floor function, and we sometimes use this notation instead, because it takes any number and it brings it down to the floor, basically. Any like a 3.8, whatever, you just cut off the 8. You're left with 3. Any decimals you have after, you basically just cut off. So if we were to graph this thing, it basically looks like this. Greatest integer function of 0, well, the closest thing is just 0. All the way up to 0.9, it would still be brought down to 0 because it doesn't hit 1 yet. But the second that it actually is equal to 1, it's stuck at 1 because the closest thing below it would be 1. Then all the way up to 1.9, it would be brought down to 1 every single time. So this is at 1. And the second that we hit 2, it jumps up to 2. All the way up to like 2.999 whatever, until it hits 3. And then it jumps up to 3 until it hits 4, but not equal to 4. This looks like 4x. I should probably erase this and put the x on top. Okay, and it works for negative values too. That's our greatest integer function. When we see the graph, it becomes a little more clear what the limit's going to end up looking like. We want to show that the limit as x approaches 3 of the greatest integer function, or the floor function, does not exist. So let's take a look at the limit as x approaches 3 from the right. Notice this is definitely piecewise. It's a step function. So it makes sense that we want to consider left and right-handed limits. So that's the limit as x approaches 3 from the right. Well, if we're to the right of 3 but going towards 3, that's like 3.5, 3.4, 3.2, 3.1, 3.01. The greatest integer function just brings everything down to 3, no matter what, when it's just above 3. So This just equals 3. Let's look at it from the left now, though. From the left, those are all the numbers that are close to 3, like 2.5, 2.6, 2.8, 2.9, 2.999. Well, again, greatest integer function drops it down to the floor, it cuts off all those decimals. We just end up with 2. So this limit is 2. So the left and right-handed limits do not match, so that implies that the limit does not exist. Does not exist. Okay, for our last theorem, we need to talk about the squeeze theorem. But first, if f of x is less than or equal to g of x when x is near a, and the limits of f and g both exist as x approaches a, then the limit of f of x will be smaller than the limit of g of x near a. So if one function is bigger than the other one, then one limit is bigger than the other one, which should make sense. So this tells us that if we have a function g of x sandwiched in between f of x and h of x, where we got these 3 functions, x is near a, we look at the limit of f of x and the limit of h of x, so we look at this limit, and we look at this limit. If they both equal L, then the function that's squeezed in the middle must have a limit of L. Because remember, it's got to be smaller than the one on the left, but it's got to be bigger than the one on the right. So it must be in between both. And if they're both exactly the same, the only way to be in between both is if it's equal to both. So that's a squeeze theorem. This function gets squeezed. It's kind of like if we have, let's say, this crazy function, and we have this crazy function. Notice they have the same limit over there. If I draw, let's say that this is h, and that this is f. If I draw another function g, it could do anything, but as long as it has the same limit right over there, this is a over here, then this function g will have the exact same limit right over here. And it makes sense because it's being squeezed by h and being squeezed by f. So how could it escape and have a different limit? Okay, let's show that the limit of x squared sine 1 over x is 0. So we can't use our product rule here, because notice the limit of x squared might exist, we could just plug it at 0, but the limit of sine of 1 over x does not exist, as we've already seen. So we have to be a little bit more creative. We need to somehow squeeze this function x squared sine over 1 over x by stumping. Well, I don't know how to do that, but I definitely know how to squeeze a trig function. Remember that sine can never be bigger than 1, and it can never be smaller than minus 1. So that means that sine of 1 over x is squeezed by 1 and minus 1. It's always smaller than 1 or equal to 1, and it's always greater than or equal to minus 1. Doesn't matter what we take the sine of, any sine function will always have that property. Okay, notice that we're near 0, but not equal to 0. So that means we're not considering x values where x is 0. We're only considering x values where x is potentially bigger or smaller than 0, which means that x squared is strictly positive. So we can multiply by it. So we multiply all 3 sides. We don't have to flip any inequalities because x squared has to always be positive. The squared kills off any negative. So I think we just figured out what we can squeeze our function by. It looks like it'll always be smaller than the function x squared and always be bigger than the function minus x squared. So let's see what those 2 limits are. It's got to be 0, right? We just plug in direct substitution. It's a polynomial. Same thing for the other one. Okay, so wonderful. Since the limit on the left, that f function is equal to the h function limit on the right, the function squeezed in the middle, g, must also have a limit that matches them. So the limit of x squared sine 1 over x must be equal to 0 by the squeeze theorem.